So, we were solving this problem, the two-dimensional problem, right, of heat conduction for the line by line TDMA method, right, or the line by line method. So, this is the example 2, right, where we said we have a domain with 4 cells, right. We call this as 1, 2, and did I call this as 3 or 4? This is 4. So, we came in like clockwise, right. So, this is 3, and T1 or TA was 100, TB was 200, and TC is 300, and TD is 400 degrees Celsius, and then we have these phase centroids, right, that get connected. Essential. Oops. Back. Okay. So, and then we have these phase centroids here, right. Is this correct? 1, 2, 3, 4, right, in the clockwise. Did we say like? Oh, I wanted to choose 2 above because we want to apply TDMA in the direction. It will be easy in terms of numbering, right. Okay. So, we had this, and then we have in the yesterday's class we have seen we have written down the linear algebraic equations, right. We have discretized and written down the equations. So, can you tell me what are the equations we have for this problem? This was 6T1 equals T2 plus T4 plus 800, and then 6T2 equals T1 plus T3 plus 1000, okay. And then what else we have? 6T3 equals T2 plus T4 plus 1200, okay, 1200, and then we have 6T4 equals T1 plus T3 plus 1000, okay, 1000, okay. That is what we have. So, essentially we have 4 equations. Now, we are deciding that we want to do, let us say, TDMA along the y direction, okay. So, this is our x and this is our y directions, and we would do guess values, or the sweep direction would be your x direction, okay. So, this would be your sweep direction, right, and the y direction would be your TDMA direction. Now, we need to guess values for the cells 3 and 4, right. In fact, we have to guess values for all of them, right, because we would be using the T3 star and T4 star. So, let me start off with guess values for T3 star equals T4 star equals I will start off with 100, okay, 100 T3 T4. I can also guess for T1 T2, but it does not make sense anyway because we are using a direct solver in that direction. So, we do not need those values because they will get anyway overwritten, right. Okay, then fine, then we have our first equation, that is this guy. This is our equation 1, 2, 3 and 4. 61 equals T2 plus how much? T4 plus 800, and 62 equals T1 plus T3 plus 1000, and 63 equals T2 plus T4 plus 1200, and then 64 equals T1 plus T3 plus 1000. Okay, so we have these equations. Now, what we want to look at is we want to apply TDMA in the y direction, right? TDMA in the y direction, and sweep in the x direction, okay. That is what we want to do. So, then for TDMA, what is that we have to do first? We have to calculate what are the coefficients P1 and Q1, right, or Pi and Qi. So, what are these coefficients for the cell 1? If we start off with 1, right. So, what is P1? P1 is B1 by, I want the expression first, this is B1 by A1, right, and then what is Q1? D1 by A1. Now, what is A, B, C, D in the expressions? A is 6, right, this is your A. What will be B? B is the one that is to the I plus 1. So, in this case it is actually J plus 1, right, we do not have. So, that is the coefficient of T2, right. So, this is 1. So, this is 1 is your B. What about C? C is 0, right. C is 0 because you do not have a connection to T0, right. So, C1 is 0. What about D? T4 plus 800, right. Essentially, whatever is remaining, this is your D1, right. That is your D1. Okay. Now, how much would these values come out to be? B1 is 1 and A1 is 6, that is your P1. What about Q1? 800 plus T4, T4 we guessed it as 100. So, that would be 100 plus 800 divided by 6, right. So, this is 900 by 6, that will be 150, right, 150, okay. P1 and Q1. Then what do we have? P1 and Q1 are there. Then what about P2? P2 would be how much? I want expression, that is B2 upon A2 minus C2 P1, right. So, we are looking at the cell 2. What is B2? B2 is 0, right, because we have to look for the cell which is in the transverse direction. So, we do not have 1, right, because here 1 is I minus 1, right. T3 is a guessed value. So, we do not have another cell on the other direction, right. So, essentially I have kind of a half figure here. Okay, let me draw this anyway completely. So, that would make it better. Okay. So, essentially for T2 cell I plus 1 is not there here, right, we do not have a cell. So, essentially B2 is how much? 0. Is this expected? If you remember, go back, we already had Bn equal to 0, right, which gave us Pn equal to 0, right. So, essentially P2 is now the last cell in the y direction in which our TDM is. So, this is expected, okay, we are not doing anything wrong, okay, this is correct, this is no mistake. Then what about Q2? Q2 expression is D2, right, plus C2 Q1, is that correct? We had Di plus Ci Qi minus 1 upon Ai minus Ci Pi minus 1. So, this would be same as A2 minus C2 P1, right, that is correct. Then what is D2? For the second cell, what will be D2? 1000 plus T3 star, right. So, that is 1100. So, this is 1100, that is D2 plus what is C2? Is there C2? C2 is what? Coefficient of I minus 1, that is 1. So, this is your C2, right. So, this is your C2, that is 1. So, we will come down. So, this is 1 times how much is Q1? 150 upon A2, how much is A2? A2 is coefficient of T2, this is your A2. So, this is how much? 6 and then minus C2 is 1. What about P1? 1/6, right. So, this is 1/6. So, how much would be Q2? This is 1250 times 6 by 35, is it? Okay. So, can you tell me how much this will be approximately? 250 is 7, 214 or something, 5, 4 something, right, 214 point something degrees, 214 point something. Okay, let us not worry about degrees. Okay. So, this is Q2, fine. Now, do we have to solve for other variables? No, we are done, right, we are done with forward substitution, we just have 2 cells, right, 1 and 2. So, we have already reached n, this is Qn. Now, what do we do? Qn equals Tn, right, Qn equals Tn. So, T2 is how much? Q2, this is 214 degrees Celsius, okay. Now, we will use the reconciliation that we already have, that is Ti equals Pi Ti plus 1 plus Qi, right. If I plug in I equals 2 in this, this is T2 equals P2, sorry, it should be P1, yeah, I want to write it for P1. So, this will be T1 equals P1 T2 plus Q1, right. So, fine. So, this is how much T1 is P1 we got it as how much 1/6 and T2 is 214 plus Q1 was 150, right? Oh sorry, not 150, how much was it? 150 is correct? Ah, okay, 150 is correct, okay. So, how much would this be? 186 or something, okay, this is 186 degrees Celsius. So, this is by guessing the values of T3 star and T4 star as 100, right. Now, can you do the same thing for 3 and 4 cells, right. Now, what would you use for T1 and T2? You would use these values, right, we are using the updated values. Now, does these numbers make sense? You have got 156 for T1, are they bounded and do they look similar? So, this we got as 186, right, and the other one is 214, do they look somewhat okay, right, it is kind of higher because you have a higher value on the upper temperature and so on. You will use these values as the guesses instead of 100, 100 for T1, T2 and then do the same TDMA here, right, and then what do? What is it after this? You come back again, right, T1, T2 and then you keep iterating until you reach some kind of a converged solution, right. Would you be able to do T3, T4 and kind of continue this process, right? You can also write a sample code, right, based on this algorithm, fine. So, that is our sweep and this is our TDMA, okay, and then we kind of keep coming to these two one after the other, right, in succession until you kind of converge, fine. Questions still now? Is it clear? Line by line is clear, yeah. Yeah, essentially in some sense, for example, you can look in terms of some kind of a norm, a L2 norm or a infinity norm, or essentially you can also look at when all the changes T1, T2, T3, T4 are less than some, the difference between T1, T2, T3, T4 is not much between the previous and the current iterations, okay. You can look it up in some kind of a norm as well, right. Other questions? 100 was just a guess. I could have started with 0 as well, okay, anything. You start off with 100. You can also start off with anything you like. Will that depend on the convergence rate? Will that definitely? Yes, it will, right. Essentially, you have guessed something very close. For example, you have taken an average of all the values and guessed it, you would probably converge quickly, right. And you have taken something very far off, then it will take longer iterations to converge, right. Now, all these things we are discussing, you can play with it once you write your own codes, right, for the 1D equation or for the 2D equations, you can start playing with all these things, okay. Other questions? Yeah, so essentially you want to start off with a guess value that is outside the bounds, yes you can, right. For example, 0 is out of bounds, right, you can start off. Other questions? But your guess value also plays a role in kind of convergence, you may actually diverge as well, that is also possible, right. So, so essentially the first solution that you would start off should also be kind of a good guess, okay. Yeah, Scarborough is satisfied, but I mean not only in this particular case, but in general if you take any algorithm, okay. No, okay, clear, fine. So, we have done the line by line method as well. Then let us move on with our next concept. So, one more thing we did not talk about is the under relaxation, right, that is something we did not talk about, essentially that is relaxation. So, this is either under or over relaxation, fine. So, in the iterative schemes that we have, sometimes we want to either accelerate or slow down, okay, the change of the dependent variable. That means the from iteration to iteration, let us say you have some phi p and you have some phi p star, right. So, this change, that is your delta phi p, is what you want to kind of control, okay. Either you want to increase it or you want to kind of slow it down from iteration to iteration, and that is what gives rise to either a over relaxation or an under relaxation, okay. So, if you are trying to accelerate this change, then it is called an over relaxation, and if you are trying to restrict it to not change that much, then it is called an under relaxation. Now, this is useful in the iterative schemes that we are using, either for if you have strongly nonlinear problems or something like that. So, in the context of nonlinear problems also, if we have nonlinear problems, now this could be either again in the nonlinearity, could be either in source terms or it could be in the diffusion coefficients and so on. So, in these cases you want to control the change of the dependent variable, okay. So, that is delta phi from iteration to iteration, okay. So, that is where we use something known as relaxation, and if you use if you accelerate the convergence, then that is known as over relaxation, okay. And you will find if you use this in the context of Gauss-Seidel, then it is known as Gauss-Seidel successive over relaxation. So, it is called GSSOR, okay. This is essentially if you want to accelerate the convergence, this is used, Gauss-Seidel successive over relaxation. You have a relaxation coefficient, that is what you would kind of tune such that you can get convergence much more quickly. Now, usually over relaxation is not useful or not used in the context of nonlinear problems, okay. So, if you have nonlinear problems, then you would go for more or often for under relaxation than over relaxation, okay. So, you will go for under relaxation. That means you do not want to have the change that is computed to be completely added, you want to kind of restrict that change, okay. That is where the under relaxation part comes into play. So, for nonlinear problems, this is what is more useful. For other problems, you can go for over relaxation to get the convergence quickly. Now, what is the, how did we find about this over relaxation? Any ideas? So, Gauss-Seidel was there, like Gauss-Seidel kind of was an iterative method. Now, how did we find out about this over relaxation in the first place? Completely by accident, right. Essentially, before the advent of computers, people were paid to kind of do these Gauss-Seidel iterations manually, right. And at that time, somebody, if they could, instead of adding delta phi to one particular iteration, they started adding more than what delta phi that is being computed, and they found that okay, you are converging much more quickly, okay. That is how the over relaxation kind of is useful, and then there is of course a lot of theory that was built in after these observations, okay. So, in terms of over relaxation and under relaxation, but the starting point was where somebody found it by accident, okay, if I just instead of adding this delta phi p, I would add 1.2 times delta phi p, and then you converge in 60 iterations rather than 120 iterations, something like that, okay. Now, these are very common over relaxation, under relaxation things in other software as well. You might see a relaxation parameter for each of the equations, right. So, you specify something like 0.6, 0.7 or 0.3 for these relaxation parameters. What they are actually doing is they are taking, let us say if you have computed whatever is your delta phi p in one particular iteration, they are only multiplying it with 0.6 and then adding it to the previous value, okay. So, that is what they are only adding this much. So, essentially 60% of what is being given from the equations is added, okay. That is what they are doing. So, essentially you are restricting the change from iteration to iteration, okay. Now, of course, this relaxation coefficient we call it as alpha, okay. This is not known, okay, as such from any theory. So, relaxation coefficient is something that is that you have to give from your experience of a particular problem, and this relaxation coefficient would depend on again on the problem statement, on the geometry, and the other parameters of the problem. Okay. So, as a result, it is not a constant value that works for all kinds of problems, rather it kind of comes from your experience of running some kind of simulations. Okay. However, there is some research that is being recently done on this alpha, we will come to that little later. So, let me go ahead with the theory of what is relaxation as such. So, if we have a Gauss-Seidel, we have our original linear algebraic equation is AP TP, okay, or phi p, okay, AP TP equals sigma A and B T and B plus B, right. So, this is our original linear algebraic equation after discretization. Now, we can rewrite this equation as Tp equals sigma A and B T and B plus B upon AP, right. I can write like this, where we are of course using some star values for the T and B, right, in our Gauss-Seidel method. Okay. Now, what we can do is I can, if I have, let us say Tp star is my previous iteration values, then I can add and subtract Tp star to the right hand side here. Okay. So, I would write this equation as Tp equals Tp star plus sigma A and B T and B plus B upon AP minus Tp star. Okay. I just added and subtracted Tp star on the right hand side. Fine. Now, what is this quantity that is in the parenthesis here? What is this? This would have actually given you what is Tp, it would have given you Tp if we had evaluated, this is Tp, and what is minus Tp star? So, this is the change in the current iteration that would have been produced, right. So, essentially this is the change in Tp in the present iteration, right, or the current iteration. Okay. Fine. So, this is the change in Tp in the current iteration for a particular cell P. Now, this is what we want to restrict or we want to amplify. Okay. Now, up till this step, okay, until this equation, this is all correct, right. Now, what I am doing here is actually changing the original equation, okay, because I am now restricting the change, right. So, that is actually changing the original equation we are solving. Okay. We will come back to the point whether we will get the correct solution or not by arbitrarily changing this delta Tp. Okay. I will come to that. So, essentially what I want to do is, okay, in relaxation what we say is we want to restrict this change, that means we want to restrict this term that is there in the bigger parenthesis. So, that will be Tp equals Tp star plus I want to multiply this with some alpha, this is sigma A and B T and B plus B upon AP minus Tp star. Now, this equation is not the original equation we have started off with, right. Until here it is the same equation, right, but then now I have multiplied with alpha which is some arbitrary constant. So, as a result I have now modified the equation, okay, but we will come back and comment on it whether it is okay to do this way or not. Fine? No? Fine? Is clear? Okay. Now, let me rewrite this a little bit. So, I will kind of take AP and alpha to the left hand side, essentially multiply this. So, this will be AP by alpha equals Tp star times AP upon alpha plus this would be how much? Sigma A and B T and B plus B minus AP Tp star. Is that correct? Oh, Tp times AP by alpha. Is that correct? Okay. So, we have AP by alpha times Tp equals Tp star times AP by alpha plus this entire quantity, right. Okay. So, I can rewrite this as AP by alpha times Tp equals sigma A and B T and B plus B, okay, plus if I were to take AP by alpha common, then this would be 1 and this would be minus alpha times Tp star, right. Essentially I am collecting this term and this term together. Is that correct? AP by alpha times 1, and here it would be minus alpha, right, minus AP TP star, AP by alpha TP star, okay, fine. So, we have done something. Okay, now we call this as the final equation. So, this is my under relaxed equation, okay, or a relaxed equation for the original equation that we have, which is APTP equals sigma n b t n b plus b. For that, this is the relaxed equation where the coefficient alpha is the relaxation parameter, okay. Fine, now we have done something, okay. Now we have to see whether this will give the correct solution or not, or are we solving the correct system or not, that is what we have to see. Now let us say at convergence, what is the value, what is the difference between TP and TP star? At convergence, your TP would be the same as TP star, which is probably differing by some epsilon. So, if that is the case, what will happen to this equation? Oh no, not 0. This equation will be there, right? There will be something here. What do we recover? So, essentially if they are the same, then I will write it down here. You have AP by alpha times TP equals sigma ANB TNB plus B plus AP by alpha times I am plugging in TP equals TP star. So, this is TP minus AP TP, right. So, what gets cancelled? These two get cancelled, right, and your AP TP, if you take it to the left hand side, right, then what is the equation that is recovered? That is the original equation. So, at convergence you are getting back your equation, okay, you are still solving the same equation as you reach convergence, okay. So, essentially the TP you would obtain for every cell will still satisfy the original equation, okay. Now, so now what have we done by doing this process of alpha? Have we changed the final solution? No. Have we changed the path to the solution? Yes, right. Instead of climbing the hill directly, we have kind of taken a D route and then climbed it, right. Essentially we have changed the path to the solution, right. So, we changed, so under relaxation only changes the path to the solution, okay, and it recovers the original linear system of equations at convergence, okay, fine. So, we get back the same system as we kind of converge. Now, any relaxation scheme that you would kind of develop should satisfy these properties, right. It should, any relaxation scheme that you have should recover the original system as you reach convergence, otherwise that scheme is not useful, right, and also for any arbitrary relaxation parameter that you would use, okay. So, that means any relaxation scheme should satisfy this condition, fine. That is what we have. Now, okay. Now, if you choose alpha in the range of 0 to 1, then this is called under relaxation, and if you choose alpha greater than 1, that is called over relaxation, okay. Okay. So, if you go back to the equation, essentially you are restricting the change, right. So, if you choose alpha less than 1, this change will be only a certain percentage of what is actually given to you by the equations, okay. And if you kind of increase this, then you are adding 20%, 30% more of what is given by the equations, okay, to get a faster convergence. Now, what is actually alpha doing when you have under relaxation? From the equations, what is alpha doing? Let us say if I have under relaxation, so alpha is between 0 to 1, right. What is it doing to the central coefficients? Diagonal dominance, right. Your AP is now AP by alpha, right. As a result, it is now larger, right. So, essentially under relaxation is increasing your diagonal dominance. As a result, it is actually helping you converge your system in a better way, right. So, essentially improving diagonal dominance. So, under relaxation is your improving diagonal dominance, or it is helping you satisfy Scarborough criteria much more strongly, right. Okay. Now, what if you have alpha greater than 1? Is it helping you with diagonal dominance? No, right. So, it is actually making it worse, right. It will not be diagonal dominant, but you can still rely on other things which are still making it diagonally dominant. For example, boundary conditions or source terms and things like that, right. For example, boundary conditions could still be probably be okay, fine. So, essentially that is the reason why I said if you have strongly nonlinear problems, then you have to kind of look at under relaxation, because the changes in the solution could be much more quickly, which it might be difficult for the system to kind of converge, okay. So, that is the thing. Yeah, okay, very good. So, essentially the question is, where will I consider the TP star term? Yeah, so where will this go? This will go into B term in the constant term, okay, and your AP is now AP by alpha, that is there, and this will anyway be, there will be some coefficients, okay. Now, this is this pattern is, or this equation is what you have to kind of use if you want to under relax or over relax any equation, okay. You have this extra coefficient, that is AP by alpha here, okay, and then you are adding AP by alpha times 1 minus alpha times the unknown here on the right hand side. So, this is your relaxed equation for the original equation for the AP TP equals sigma NB TNB plus B, okay, fine. So, you would use this equation whenever we refer to a relaxed system for a given equation, okay. You have these two extra terms, which is you have 1 by alpha on the left hand side, and you have this term AP by alpha times 1 minus alpha times the dependent quantity for that particular cell, okay. Now, as we discussed before, there is no thumb rule for how to choose alpha, okay, but it kind of comes from experience, okay. So, usually you can take, if you want to under relax, you probably take it as 0.6, 0.8 or whatever, okay, or it could be much smaller as 0.3, 0.2 as well. So, essentially you are restricting the change, right. So, if you make alpha tend to 0, what will happen to the convergence? It will be very slow, right, because TP would not be very different from TP star, it will be very slow, right. So, if you make alpha close to 1, then essentially you are making it same as the original system, right. If it is greater, then you have a larger changes coming into play, okay. So, these are the limits. Now, recently there has been some renewed interest in coming up with how should I calculate alpha, okay, or should alpha be the same for all the iterations, or can I change it with iterations? You can change it with iterations, but we just do not know how much to change it, okay. So, but you can certainly do that. You can start off with alpha which is small value 0.3 or something. After, let us say you feel the solution has evolved somewhat into a better physically correct solution, then you can increase the alpha so that you can reach convergence quickly. All these things can be done, but many a times calculating what values alpha takes could be as complicated as actually calculating the solution itself, okay. That is like actually solving for two problems. So, that is why you do not kind of dwell too much into what alpha should be and how should I use it, what should I take it after so many iterations. So, that will basically make it computationally as expensive as solving the system, okay. So, rather you are more happy just go and solve the system with some alpha than actually trying to see what is this alpha value should be, okay, as expensive as solving the system. But there has been some recent renewed interest, and then some recent research has shown that you can actually have certain values of alpha, okay. So, essentially what alpha value should I take and how do I kind of change them for a given problem. This is recently known as the Gauss-Seidel scheduled, or not the Gauss-Seidel, it is just called scheduled relaxation Jacobi. Okay, it's called SRJ, scheduled relaxation Jacobi, which will tell you what alpha to use for what kind of problems. Okay, and then how should you kind of pattern it. You know, what are the values you should use as you go with iterations. This basically will come out as a if you kind of go through this research papers that are there. If you look up for scheduled relaxation Jacobi, you would get them. Essentially, it will basically become a minimization problem to calculate alpha. Okay, so this was done in the past, and it was shown that if you pattern alpha in a certain sequence, then the scheduled relaxation Jacobi will converge much faster than Gauss Seidel SOR and things like that. Okay, so we are not going to this as of now, but it's kind of information for you. If you are interested, you can go and look up all these things. Fine. Otherwise, it kind of depends on experience and the problem you are solving. Okay. So in your assignments or projects also, you will use under relaxation when you have strong nonlinearities. Okay. In which case, you will modify the system like this, and you would use some alpha value, which will be either told to you by in the assignment or something. Fine. Questions? Questions on this part, on the under relaxation and over relaxation? Yes. In case of so what is the upper limit for alpha in case of over relaxation? Essentially, there is no upper limit, but the issue is if you use very large values, it will just diverge. That's the thing. The solution will diverge. Usually, you don't see more than like 1.2 or 1.1 because it's kind of adding 20% more than what it is supposed to be, right? Right. Yes, you can. Yes, that is possible. So essentially, can I increase the diagonal dominance by using under relaxation? Yes, you can. Right. Yeah. Essentially, what is the advantage of under relaxation? It will help you satisfy diagonal dominance, and strongly nonlinear problems can be solved. Right, because you are changing the path to solution. As a result, your algorithm will not diverge. Right, your diagonal dominance will be preserved at every stage. Okay, you will see that actually. Maybe in the assignment, if we have one problem, you can see if you set alpha equals 1, you will see that it starts diverging after certain values because the diagonal dominance will not be preserved. Otherwise, you will have the diagonal dominance maintained throughout the solution. Right. Other questions? Yeah. Right. Okay. So can I try over relaxation, knowing that the Scarborough is satisfied with by other means? Yes, that is quite possible. That is where actually over relaxation will be used. You know that you have a kind of a not very strong nonlinearities, and you have boundary conditions are helping you with the Scarborough. Then you can go for some kind of over relaxation. That is possible. Right. Okay. So that's about the under relaxation part as well. Did we write an algorithm yesterday for the source term linearization? How do we calculate? I guess we didn't, right? We just calculated the source terms and how to kind of do it. We did not write an overall solution algorithm, we didn't do, right? So let me kind of finish that part. So essentially, if we have source term linearization, this is important because you have to update the coefficients SC and SP as part of the solution loop. Okay, so it's a small algorithm. Okay, so if you have then how do we do it? Essentially, you first guess either the phi star values, right, or the t star values depending on the problem. Then you would calculate SC and SP, right, and of course you would also calculate what is your essentially also discretize the equations and come up with the linear system, right. Then what do? You solve for the system of linear equations. Okay, solve for the linear system. Okay, Then once you have solved it, what do you have to do? We have to update the values of SC and SP, right. So now this step 4 here is not convergence. Why is it not convergence? Because SC, SP are now modified, right. We were given some nonlinear equation, we have comfortably made them linear and then we solved something. So as a result, the solution we get out of step 4 is not the solution to the original problem we wanted, right. As a result, you see we are now introducing an iteration, right, on top of the iterations we might have had in step 4, right. If you had used a Gauss-Seidel, you are doing iterations in step 4, right. Now I have another iteration that I am doing, which I would like to call it as an outer iteration, right, which is coming out because of non-linearities in the problem, because we have linearized the non-linearities. You see that? So essentially here what I do is I update SC and SP, because now these are now functions of temperature, right. These are now functions of temperature and the temperatures just got updated in step 4, right. So I will go here. Now what do? I kind of repeat till convergence, right. So that means I go back and then once with the updated values I will go to step 4 and then update the coefficients, then solve for the system, then come update the SCSP and so on, and then once you reach convergence you can stop. So do you see 2 loops here? There is one loop here which we call it as an inner iteration loop, okay, and there is an outer loop, that is this guy, this is the outer iteration loop. This is coming because of the non-linearities, okay, or essentially this is coming because of the non-linearities, right, which you cannot avoid as long as you have non-linearities, okay. Now we had one question, I think in the previous lectures. Let us say if I use a direct system to solve Ax equal to b, I would use, then where will that go? That only goes into the inner loop, right. So this will be a direct solver, but still I have to have a iterations, right, for the outer loop, right, because of the non-linearities, okay. So keep these things in the your, I will just come to that. So essentially we have 2 loops, one is inner loop, this is basically because of your Gauss-Seidel or because of an iterative method we are using, and we have this outer loop which is required because of the non-linearities. Now later on we will see that this outer loop is required not only because we have non-linearities, but also if you have inter-equation coupling. For example, let us say you are solving for momentum equations in x and y directions, so you have u and v equations for Navier-Stokes, then while solving for v equation you are using u, but u are actually guessed values. Similarly, while solving for u equation you have a flux coming from v, so v are guess values. So if you have inter-equation coupling, then you still have to use iterations, okay. We can solve for, let us say, a system of linear equations, linearized system, but still if there is inter-equation coupling, then the coefficients are provisional, right. So whenever you have coefficients are provisional, then you need an outer loop to converge it to the correct solution, okay. So outer loop comes even if you have inter-equation coupling. Usually if you have more than one equation, there will be some kind of coupling between the equations, right, otherwise there is no point in solving for 2, right. So there will be some coupling. So inter-equation coupling also gives rise to outer loop. Non-linearities in the source term, diffusion coefficients, or in the terms itself. For example, convection term, right, is a non-linear term, right. You have del dot rho u bar, right. So the convection term, all these things will give rise to an outer loop, okay. Yes, questions? You have to check for, convergence is basically you will always check for between TP and now there is not TP and TP star, there is also another TP outer, right. You see that? So there is one TP star to check for convergence of the inner loop, but there is one more TP old, that is what you have started off with, right, that is also there, because if you check with TP and TP star, everything is fine, you have converged, you will just come out, right, that is not correct. See that? So you have TP old which you have started off here, right, essentially compare with this T star, right, and then we can call this inner loop as T double star, okay. You see that? So, that value should be converged, right, should not change more than some epsilon. Is that clear? The difference between outer loops and inner loops and things like that, okay, fine. Okay, then we have kind of finished these parts. So, the next concept is basically going back to the diffusion equation. Up till now we have applied it for Cartesian meshes, right. Now, the same methodology that we have developed can be applied for other orthogonal coordinate systems. For example, if you have polar coordinates or if you have axisymmetric problems in 2D, the same methodology can be extended to all other orthogonal coordinate systems. So, we are going to see how to solve it on a in r theta coordinates for a polar, in polar geometry, and also for axisymmetric geometries and things like that in the coming lectures. After that, we will move on to unsteady and then to unstructured meshes and so on. Okay, we are still dealing with the diffusion equation. Okay.